Continuing on with the Carnot cycle, here's some images and way too many words from Sengel, where they walk through what a Carnot cycle might look like on a PV diagram. So the pressure versus volume diagram, and you can see that we have a isothermal process coming from 1 to 2, and then we have an adiabatic process expansion going from 2 to 3. And then we have heat rejection, which is another isothermal process down to the sink. And then we have an adiabatic compression to come back to 1, and now we have our cycle. So this is the best efficiency that you can get. And these two propositions for the Carnot cycle. First proposition, it's impossible to make an engine that operates between two given reservoirs, right, the heat source and the heat sink, and is more efficient than a reversible engine operating between these same reservoirs. So we have this idealized thing, this reversible, the Carnot cycle, and it's impossible to achieve the Carnot cycle. It is the best that you can possibly do. And the second is that all engines that operate on the Carnot cycle between these two reservoirs, if it is a Carnot cycle, it has the same efficiency. Basically, I think here's what I want to say is that this temperature scale. All right. So what I want to talk about in this topic, the thermodynamic temperature scale, without like going into a lot of detail into it, like hardly any detail, is that the ratio of these heats, the ratio of the heat and the high heat to the low heat is going to equal to the ratio of this high temperature to low temperature. And so that's like this thermodynamic scale that we're going to be using. So what we're saying is this temperature scale is independent of the substance, and that we can also think of this as the absolute temperature scale. So where we had the thermal efficiency in general, and this is for a pretty simple cycle type of thing. We said at 1 minus Q L over, excuse me, okay, let me erase that, sorry. I got distracted. I should just start over, but I'm going to keep going. Come on. There you go. We had QL over QH. All right, so now using this thermodynamic temperature scale where we're going to ignore what the substance is, we could say that here's our Carnot cycle. So here I wrote it at the end of the last video. We're going to have 1 minus the low temperature divided by the high temperature. And what's important here, I think, is the simple presentation of this idealized cycle. The idea here is like, well, if you want to improve your efficiency, increase the high temperature reservoir. You want to improve your efficiency, decrease your low temperature reservoir, which can be kind of a challenge. But if you, like on a colder day, you'll have more efficiency than on a hotter day, all things being equal in terms of the engine and that type of thing. There is truth to that. So let's see. I want to switch over to paper, and there's some derivation going on here, but it's good for you. So we'll just go ahead and do it anyway, even though we don't like it. All right. So I wish I had made these notes reformatted a little bit, and I even wrote at the top of mine, rewrite the blank notes, but I'd already published this by the time I filled it out, and well, that's just how it goes. All right. So we're going to start out with the ideal gas law. All right, so our cycle, everything from here on out, is limited to an ideal gas. So all these equations that we're using from this are all limited to that. And then here is our first law right here. Right, so there's the heat, and this is for a single substance, so a single chunk of mass coming through here, not a steady flow system right here. So you recognize that's the same thing as U2 minus U1 is equal to Q12 minus work 12, right? So that's a heat in, work out, change in internal energy, but here's just a small little tiny incremental changes. And we could say that the incremental heat change, all right, so okay, should also place in here, by definition, of the specific heats right here, we have du is equal to CV dt, right in there. And we can also, from the work right here, right, so we're going to do 2 steps for this one. We're going to say, now remember that d work is equal to pressure, and this for a constant pressure. Well, we're doing a little integral, so this should be 2 dV, right? So work is integrated. We can integrate this right here to get work, right? So these are on a per mass basis. That's on a per mass basis. And then we can go ahead and take and substitute the pressure right in here, right? P is going to be equal to R over RT over V. And we can go ahead and we can say that we get this equation right there. So this equation, I just wrote it down there, but I wanted to make sure we knew we could affirm that we could say that this dQ is going to equal to CV dt, constant volume specific heat for the internal energy, and for the work is P times dV, which we could substitute the P with this right here. So you can see that we have, this is V and we have V, so we could do the integration there. So that's fine. So we start out with an isothermal, and by the way, this is this is kind of in a weird spot because we're going to do this and we're going to find that, right? And the same thing true here in terms of what's on our page. Here is what the results are going to be. I've already written down what the results are going to be, and we can see what the curvature looks like for these processes. All right. So the isothermal heat addition that goes between 1 and 2, which is right here and right here, it's isothermal. So therefore, when you go to, we'll use this equation and go, here's our heat addition between, let's say, 1 and 2. Is going to be, well, there's no temperature change here, so it's isothermal. So all we're left with, and this is constant temperature, so this gets to be brought out to the outside. So if we're doing an integration between 1 and 2 of this heat right here, there's no term here, so we can just leave it off. So here's our 0 right there to represent what happened right there. And then we'd have RT, and then the integral of 1 over V dV, going between states 1 and 2. So you take a look up here, you see, well, you get a natural log from this. You know, the integral of 1 over something and is going to be a natural log, and states 2 to state 1 because going from 1 to 2. All right, so we're good right there. We can call that 1. Then we come from the adiabatic expansion, which is coming from 2 to 3. Another reversible process right here, but it's adiabatic. So the Q over there gets turned to 0, right? So there's 0 equals up here in that equation. And so we do have a temperature change that's going to take place, but that CV is constant. So we could bring him to the outside and integrate that. And once again, you get 1 over T dt, right? And this is going to go from, let me see, this is going to go from states 2 to 3, right? And then we are also up in here, the T is constant, no, not the T isn't constant, right? No, I know what we did. I'm sorry. I made a mistake. Okay, so let me just go ahead and say, just a moment. All right, so what I should have done, I made a mistake here. I forgot to mention that because I want to get rid of that T, so I'm going to divide all of the way through by T, right? So that's where that 1 over T came from, right? And we didn't have a 1 over T here until we decided to divide both sides by RT. So we got rid of him by bringing him over there. And then we're going to go plus R is coming to the other side right here. And then we're going to get integral of 1 over V dV again. So we get the, kind of a similar thing going on here. So this is going to be, again, 2 to 3. And so what you're left with, because we don't know the function of T, we don't know how t necessarily functions, whether it's going to go from the high to the low right here. I guess that's my explanation. I think I would have made this a logarithm, but that's okay. But this is a logarithm because we know we're going between these two. I think that's the best way to say it. So anyway, we end up with a 2 right there. And then, this is also going to be helpful. I know. This is also going to be helpful to leave this alone for a bit because I will actually want to flip the sign of this in a second. That's it. Now we have the isothermal rejection that's going to go from between 3 and 4, right? So we're rejecting heat, but we're also moving it. We're also, there's some compression going on because we're moving from this volume down to a smaller volume. So that you can see that it's moving in that direction. So once again, we're going to take the integral of this guy up above, and that time now it's going to go between 3 and 4, and so we're moving there, and it should be a del. I'm sorry, it should be a del right in there, just like there's a del right there. Del Q between 3 and 4, and this is going to be, this should be negative, right? So the nature of the thing should be negative, moving in that direction. So you could put the negative in either spot, I suppose. The temperature is not changing because it's isothermal right here. So we can, I guess we put a -0 right there. So put a -0 right here. But now, once again, the temperature is constant. It's going to be the low temperature. So we can move that, the R and the T on the other side, and because this is heat coming out of the thing, that's why this is negative. We got R and T, and then we got the integral of 1 over V dV as we're moving to the thing, and then once again, this is going to be 3 to 4. Right, so here's how we get, and by the way, this is the low temperature, and maybe we would have labeled this the high temperature right in here. And then so that's going to be this guy right here. And then lastly, we're going to have like 0 is equal to CV dt. But we're going to divide the whole thing by t again because we want to move this t out over to here. So we're going to have the integral of CV over t dt, and then plus the integral, well, R because it's a constant, right? And we got rid of the T because we divided through by it. And 1 over V dV. And so this is end up going to be a natural log as well, right in here. But we're going to keep this by going from 4 to 1 in that direction because we want to get rid of the signs. This is sort of a proof of the previous the previous statement of this, right? So we had this statement, and like, well, how did you get to that? This is the reason why we're doing it in the long way around. I'm saying it. So we have this. All right. So now let's say that we want to get from compare 2 and 4. So compare 2 and 4 together. These two things right here. So at first we have, flop this onto the other side of the equation right here. So we'll say that going from TH to TL, CV over T dt is going to be equal to a negative R natural log V3 over V2. Which we can also flip the sign and go R is the natural log of V2 over V3. All right, so the sign got flipped right here by flipping which direction we divided that. So, and then go ahead from, so let me see that. Okay, now let's go ahead up to 4, right? So this is from 2. And this is from 4. And from 4, we want to get them on either side of the equal sign. So once again, we had the TL, TH, and that's a CV over T dt. And you see that they're looking very similar to each other now, except that this is the wrong flip. It's going to be equal to negative R natural log V1 over V4 type of thing. And just taking a look right here. Okay, so now we can go, if we want to flip our sign again, so we want to flip our sign. Let me see. Oh, we could just flip the order in which we do these, right? Which is going to flip that sign. So we go TH to TL, CV over T dt, and now that's changed the sign to R, L, L, N, V1, V4, right? So what we've done in here is we've made this one and this one the same. So we can set these two equal to each other. And what that's going to do for us is going to say V2 over V3. We go therefore, setting that one and that one equal to each other. That means that and that are equal to each other. And that means that V2 over V3 is equal to V1 over V4. Now, these are just a ratio right here. This is what we just said. Okay, well, and by the way, that could probably have been, no, that could not have been proven, right? I was about to say that could be proven just by looking at this, but it's not necessarily true. You wouldn't know that by looking at here. There's nothing that says that these two volume ratios of these are going to be the same until you have done this right here to say that these are related to each other, these volume ratios. But we could just mess around with this a little bit, rearrange this, make 3 go on top and 1 go on the bottom over here. So we could just rearrange and say that V3 over V4 is equal to V2 over V1. All right, so we did a lot of interesting things as part of this, but really doesn't seem like anything we did kind of mattered there. Well, let's go back to what efficiency is, the thermal efficiency. In general is 1 minus, and we usually use big Q's, but we can do it on a per mass basis, so this is just the same thing right there. And usually use capital H, there we go, low and high, right? So there's thermal efficiency, but let's go, we know what QL is, and we know what QH is from up here, from the Carnot one. We have this QH here and a QL here. So let's divide these things through, right? The signs don't matter to me. I don't know why we had to do the stuff with the signs up here. I would have left those out right there. But let's just ignore the signs. And so put this in here. 1 minus QL as defined up here is going to be RTL natural log of V4 over V3. All right? And so that's our QL. Now we get to QH. We need to look back up at the top. The QH is RTH, natural log of 2 over 1. RTH ln of V2 over V1. But we have just established right here that those two ratios are the same, so they can cancel each other out, right? Oh boy, wait, did I write that wrong? That should be 2 over 1, and should that be 3 over 4? That should be 4 over, oh boy, 1 second. Let me double check that. I don't like, I know I must have made a mistake. 1 second. All right, so here it was. The sign did matter up here, okay? So that sign right there, we don't want that sign. We want it reversed. So that means that's got to flip for that sign. So we wanted a QL in there and what its innate sign was supposed to be. So that means that QL had to be 3 over 4. V3 over V4, and therefore that's where we were able to get this ratio, that 3 over 4, 2 over 1. Able to get rid of this, able to get rid of that, and we have this is now applicable only to the Carnot cycle, and it is the efficiency 1 TL over TH. And so we're kind of using like sort of a thermodynamic temperature scale for that. And that was painful, but we got to the thing we wanted to do. right, was to establish this main equation out of derivation of these main foundations. And remember that this whole thing will work for, the theoretical calculations will work right here when comparing stuff, because this is idealized. We're trying to use what the ideal is and approach it. But in the development of it, we needed to assume that it was an ideal gas and use the first law, and then use constant specific heat here. And of course, that was the ideal gas placed into there. Go through these processes and make sure that they're all reversible. And now we've constructed our ideal cycle. And anything we do beyond that, anything that we want to compare with that, is always going to be less. We can't get any better than this.